Well, friends, here's a video on what we're doing today in class. In general, it's on length contraction. If an object is moving at a speed v, it appears to shrink. So its length from an outside perspective we call L prime. And L prime equals its normal length in its own rest frame over gamma. Remember, gamma is always greater than or equal to 1. It equals 1 when there is no velocity, and it's greater than 1 and it approaches infinity. As v approaches c. So what does that mean? It means that, so L prime is how long moving object appears in the direction of motion only. So it's not going to shrink like in all dimensions. Only in that one dimension is its motion. So in the dimension of motion is the only place that this effect has any. So if you were to measure its length, the measurement you would take makes it, you would measure it, and that measurement would give you a result that's smaller than if it were still, or that it would do in its own reference frame. So how long moving object appears to outside observer. Now, here's a really important point. And L is length in rest frame. Length when it is at rest or in its own frame. How I'm going to ask this, and the proof of this is pretty easy. The proof of this is actually where, and this is how I'm going to ask this, if the object is moving and there's a platform that in the platform's rest frame is stationary, that's L. So the platform isn't moving, so we have the train moving. The platform is not moving. But so this is the outside frame, Earth frame. Really, I should just say Earth. Yeah, I'll just say outside. Great. But what does the train see? The train sees that it is stationary. So I'm not talking about the train's length. If I was talking about the train's length, it's easy. The train's length that I would see if I'm on the platform is its normal length divided by gamma. So you always have that the length gets shorter. That's what you can always remember, that the moving object is shorter. It's smaller. So please keep that what's the word, consistent, straight. If you do that, you're good. All right, there's ways to keep this simple, so you're not sitting there confused with which is which. It takes a minute to take that minute, right? L prime is always less than L. Here's the formula. What the train sees is the platform is moving. Remember, if you're running, the Earth is running towards you. Please enter that reference frame, guys. Do it as much as you can. Enter it. It's the connection. It's that realization that can come from this. You know, we're doing equations on the board. Get lost in the math. To make it real, when you walk down the street, visualize that you are always at rest. relative to yourself, enter that space. And that is the gateway to seeing this. And the point is that when this object is moving in its frame, the platform, when you're in a subway, the platforms are all coming toward you. And so it's going to measure the platform as some length L prime. So now the platform becomes the moving object in the train's reference frame. Take a moment to let that make sense. And the point is that the train experiences a time t. And here the outside observer experiences a time t prime. So that explains why the t prime and the L's have different values. So the train experiences time t, but sees the platform outside of itself as L prime. So they're both going at the same velocity, which is kind of cool, right? This reference frame shift makes it that these are the same velocity. So what's velocity? So velocity is distance over time, L over t prime. Here velocity is L prime over t, and so those equal each other. And t prime is gamma times t. Right? So these pictures lead to this, these lead to this, and this leads to this. If you can follow my formulas here. And look, the t cancels, and I get that L prime is L over gamma. So that the length actually appears shorter because this time is smaller. Same velocity, this is a smaller time. So this is a shorter distance. See? Yeah, that's actually the whole point. So what we're doing today is, so say I have Earth, Sun, separated by a distance of 150 million kilometers, which we call an astronomical unit. That's also 8.33333 light minutes, 8 light minutes and 20 light seconds. Now, what does that mean? Here's what it means. So the speed of light is 3 times 10 to the 8. You're not going to have to actually do these conversions necessarily, although you should know how many minutes, seconds there are in a year, or in a minute, or in an hour, for doing our time dilation, as we did in class the other day. So for instance, if I say, okay, that's the speed of light, and I have a time of 1 year, how far does light go in a year? Well, it goes 1 light year. So distance is velocity times time. So we have new units. Right. So instead of, I can do meters, right? 1 year times 365 days. You can do 0.25 if you want, because it's a leap year, but I'll just do 365 times 24 hours in a day times 60 times 60. So new units. So units number 1, meters and seconds. Units number 2, we have light years, speed of light, and years. Or light minutes, speed of light, and minutes. Or light hours, speed of light, and hours. You can talk about it in terms of the speed of light. This is L, by the way. L, Y, R, C, years, light years. So what I'm doing is I'm doing the seconds. So this is number of seconds in a year equals 31 million. Get my calculator here. 365 times 24 times 60 times 60. Right? 31,536,000 seconds in a year. So what I could do is I could write distance is the speed of light in meters and seconds times seconds. And I get that 1 light year is this many, 9.4608, just to be exact, times 10 to the 15 meters. So 9.46 thousand trillion meters. And that's about a quarter of the way to the nearest star. So if you're doing space travel in real life, and that's kind of where we're going, is like, what does this look like realistically? If you're actually going to go to Alpha Centauri, or Proxima Centauri, the nearest star, it takes 4.26 years to get there at the speed of light. So if you're actually, and people are actually figuring this out, you know, the distance between stars is so huge. How do we even get there? It's hard enough to get to Pluto. It took 10 years to get there. So you can say distance is velocity times time like this, or you can say 1 light year is the speed of light times 1 year, where it's 1, 1, and 1, meaning you have 1 light year equals 1 c times 1 year. Which is easier? I'll leave that up to you, but I'm going with this one, right? So the new unit of distance is a light year or a light minute, and the new unit of velocity is in terms of c. So for example, if I'm going 8.3 light minutes at, let's say I'm in a rocket ship. This is my rocket ship. It's a triangle ship, rocket ship. And I'm going at half the speed of light. I'm not going to plug in 3 times 10 to the 8 meters per second. I'm going to plug in 0.5. So my velocity is a half of that, 1.5 times 10 to the 8, but I'm not going to do meters and seconds. I could. I know the kilometers distance, right? So the question is, from Earth frame, I'm going to do Earth frame over here. What is t, and what is the distance? So t prime is the rest frame, and L is this distance. This is L. Because the space, you can think of space as being at rest here. Although space doesn't have, I don't know. You can think of like a string attaching the Earth to the sun, right? L is 8.3. You can put the bar over it, but I'll just do 8.3 light minutes. I'll do 3 bar to be more exact. Light minutes. T prime is what? Well, T prime is distance over velocity. Distance is 8.3 light bar light minutes over velocity 0.5. So I get what? 16.6 bar minutes. What does that mean? Pause and think about what that means. Time for T prime is the amount of time it takes for the rocket, time observed from Earth for rocket to reach the sun. So I would observe, I am going half the speed of light. It takes light 8 minutes. That's crazy, by the way. Right? Count to 500 seconds. This is 500 seconds. Right? So it's 500 light seconds. That's another way to say it. If you count to 500, that's how long it took those photons to reach your face from the sun. If you're going at half the speed of light, it takes twice that amount of time. Great. But if you're in the rocket ship, what is the rocket's perspective? So first of all, the rocket experiences less time and experiences less space. Both are less. So T is less than T prime, and L prime is less than L. Now be careful. What are T and T prime and L? So T is the observed time inside the rest frame of the rocket, which is moving, And this is how much it observes space, the distance from Earth to Sun, to shrink. Because from its perspective, this is all from rocket's perspective. This is not the length of the rocket. This is the length of space itself. So that's why I'm switching it, right? Rocket's perspective. When I say length, I'm talking about the distance from the Earth to the Sun. That's not the rocket itself. So I'm not talking about what is the rocket's length from our perspective. I'm saying what is the distance to the Sun from the rocket's perspective. The rocket actually sees the distance to the Sun shrink. That it's like it brought it closer to itself by moving. And I think that's amazing that just by moving, distance actually shrinks. And I'm not saying like, okay, you're bringing it to yourself because you're moving. It's like if you move faster, space actually appears to shrink. That you measure space to be smaller in that direction of motion. And I think that's profound. So like, right? Do with that what you will. See if you can visualize it. We're going to try to draw it, but this is real. And T is going to be what? Well, it's going to be T prime over gamma. And this is going to be L over gamma. So less time, less space in the rocket. Great. So this is going to be, what is it? 16.6 bar light minutes over gamma. And this is going to be 8 1/3 light, sorry, this is minutes and this is light minutes over gamma. So what is gamma? So we probably should have started there, where if I have any speed, I can write gamma equals 1 over the square root of 1 minus v squared, 1 over 0.5 squared over c squared. And the c squareds cancel if I'm in the speed of light, which is really nice. And that's going to equal what? I got my handy calculator out. Try it right now. Let's have a calculator with you. 0.5 squared, 1 minus that, 0.75. Square root of 0.75. It's 0.866, but be careful, it's 1. Wait a minute. Yeah, 1 divided by that. That tripped me out for a second. Because we got 8.866 as velocity the other day. Anyway, this is a gamma of 1.155. So 1.66 divided by 1.155. And this is 8.33 divided by 1.155. Great. So I get that the time that the rocket experiences is about 14.4 minutes. And the distance that it sees from the Earth to the Sun is about 7.2 light minutes. So the space, and by the way, half the speed of light, gamma isn't that much. That's like 1.155, that's like 15% change. 0.155, right? A little bigger than 1. Half the speed of light, you're not getting much of a change, but space actually would be measured to be that much shorter. And that actually explains time dilation from an interesting perspective, that the rocket appears space to move. So if you're moving at half the speed of light, right? From my perspective, you appear to go a certain distance, length, in a certain time, t prime. But so this is Earth's perspective, right? But from the rocket perspective, the rocket actually experiences a little bit less space by about 15%. And therefore a little bit less time. And space itself is moving at that speed of half the speed of light. So you can think about it when you're moving from the Earth to the sun, is that space is moving past you, and space is shortened. Therefore, your time to get there is shortened. You say, hey, I just got there in a quicker amount of time because it was less space. Distance equals velocity over time. What's cool is when you switch reference frames, the velocity stays the same. Cool, right? Amazing. Other example, muons in the atmosphere. Here's the Earth. I don't want to do it like that. Here's the Earth's atmosphere. Atmosphere is a thin shell about 100 kilometers. Is what's called the Kármán line, the border to outer space. It's roughly estimated to be around 100 kilometers. Muons generated in the atmosphere should decay in, from their reference frame, they should decay in 2.2 microseconds. A micro is times 10 to the negative 6. But they're actually observed to decay in 220 microseconds, which means they actually make it to the surface of the Earth. So that means their gamma is 100, which means how much length do they experience of the atmosphere? Well, their length of the atmosphere is going to be 100 kilometers. This is L because it's at rest. Right? And L prime is what the moving object sees, right, this to be. So over 100, which is gamma. And so I get that L prime is 1 kilometer, which means the muons see the atmosphere as 1 kilometer. Muons. It's a muon. Muons see atmosphere as 1 kilometer deep. That's kind of crazy. So in their reference frame, they're only taking 2.2 microseconds. So from their reference frame, 2.2 microseconds, they exist, and then they decay into electrons, as we showed via the weak interaction. But from our reference frame, they're moving, so their time is longer and our distance is longer, because on our reference frame, the length is longer and the time is longer. I just think it's crazy. And this is real. This is actually how we can detect muons, because otherwise we wouldn't be able to detect them. So they see it as a shorter atmosphere. That's it. If you get that, you're good. I would say stick with that, look at that, review it until it starts to make sense. Cool. Have fun. Ask me any questions if you have them in any form at any time. Have a beautiful day, guys.